Alright, so today we're going to be looking at Physics Paper 3. This is the core theory paper. This is for May-June 2017. The code for that is 0625/31. This is a CIE Physics exam.
Okay, let's get going.
Question 1. A pipe drips water into an empty glass jar. A student takes measurements to find how fast the water is rising up the jar. Figure 1.1 shows the arrangement. Okay, so we've got pipe, water dripping into a glass jar. Good. The student measures the depth of the water every minute. State two pieces of equipment that she uses. Alright, well, she's measuring the depth every minute. So, for the depth, you're going to need a ruler. For every minute, so you're going to need a stopwatch. There we go. And there we go, let's write those down. Ruler, stopwatch. Could just use a clock, just something that'll give you an accurate measurement of 60 seconds. Part B. A student records her observations in a table. She then plots the graph using the axis shown in figure 1.2. Alright. Label both axes with a title and a unit. Alright, well, time is our independent variable, time t, and that's being measured in minutes. We're measuring the depth every minute. We're not measuring the time every time it goes, say, a centimetre deeper. We're measuring the depth. The time we're using is not dependent on anything except just the random passage of time. Alright, so time t in minutes, our independent variable, goes on the x-axis. The depth being measured in millimetres goes on the y-axis. That's our dependent variable. Let's see what the next part of the question is. On figure, part 2, the water rises up the jar at a constant speed. Draw a line in figure 1.2 to show the student's graph. Start the line from the time when the jar is empty. Alright, well, we're expected to see the water go in at a constant rate, so what we should have is a nice straight line. There we go, beautiful. Straight line graph starting from 0, 0. C. A puddle of water forms on the ground. The average depth of the water is 2.5 millimetres. Determine the average depth of the water in metres. Alright, you know what, let's just do this. 2.5 millimetres can be rewritten 2.5 times 10 to the negative 3 metres. That's what milli means. It means multiply by 10 to the minus 3. So that's the answer. 2.5 times 10 to the minus 3, and the units are already here. There we go. So 2.5 times 10 to the minus 3 metres. 2. 3 racing cars, A, B and C, all accelerate steadily and then continue at a constant speed. Figure 2.1 gives information about the movement of car A and car B at the start of the race. Okay. State the maximum speed of car A. Alright, well, looking at this, here we are, that's 35 metres per second, and that's the answer for the maximum speed of car A. There we go. Calculate the distance travelled by car B when accelerating. Ooh. Alright, it's accelerating. Remember, acceleration is change in speed over change in time. Technically it's change in velocity, but we're dealing with a speed-time graph here. Alright, so change in speed divided by change in time. The speed's changing up to here, and at this point it stops changing. So we want to find the distance travelled when it's accelerating. It's going to be the distance travelled up to this point. There we go, so that's 15 seconds along here. And if I mark it on the y-axis, it's 25 metres per second there. Now why have I drawn that? Okay, well, because this area here, the area under a speed time graph, is the distance travelled. And what I've got is a triangular shape. So the area under a speed time graph is the distance travelled. We've got a triangular area up there, let's use that. So the area of a triangle is 1/2 times base times height. That's 1/2 times 15 seconds times the height of 25 meters per second. Which gives a value of 187.5 meters. Make sure that decimal point's nice and visible. There we go. Part C. Car C has a greater acceleration than car A, but it reaches a lower constant speed than car B. Figure 2.1, draw a line to show the movement of car C. So let's draw a line to show what it could look like. It's not given us any information, it's just no numbers. It's just said, hey, you know what, it accelerates more and it ends up going more slowly than B. So what I'm going to do is I'm going to create one that accelerates faster. There we go, we get a steeper line. And by the time it stops accelerating, it's got a lower maximum speed than B. There we go, travels at constant speed after that. Perfect. So the only two things we had, larger initial acceleration and the constant speed at the end is lower. There we go. Question 3. Figure 3.1 shows a tyre hanging from the branch of a tree. Alright, it's 2.5 meters out. The mass of the tyre is 15 kilograms. Calculate its weight. Alright. Said this in most of the videos where it comes up. I'm going to say it again. Calculate its weight. If you're ever unsure what value to use for the weight, go to the front page. It's always written in the front page of these exams. There we are. Acceleration of free fall, 10 meters per second. That is the value for gravity. And now we're being asked to calculate the weight. There we go. Well, weight equals mass times gravity. We know the mass is 15 kilograms, that's been told to us, and gravity is 10 meters per second, -2, which is 150 newtons. 150 newtons, the units are already there, so that's fine. The weight of the tyre exerts a moment on the branch about point P where the branch joins the tree. 1. Explain what is meant by the term moment. Alright, a moment is really a turning effect. So a moment is a turning effect. 2. A child sits in a tyre. The weight of the child and the tyre together is 425 newtons. There we go, key point. Calculate the moment of this force about point P. Use the information given in 3.1 and include the unit. Ooh, alright. Let's do this. Well, first things first, what do we know? We know that moment equals force times distance from pivot. Which gives us a force, in this case we've just been given in this question, 425 newtons, multiplied by the distance from the pivot, and the swing was 2.5 meters away from the pivot, 2.5 meters away from the end of the branch where it joins the tree trunk. And that gives us a value of 162.5. Now here's a question. If I take newtons and I multiply it by meters, what does it give me? They're not joules, not kilograms. I've got newtons, I multiply it by meters. You know, if I don't know, all I have to do is write down it's newtons multiplied by meters. That's literally it. That's the answer. 1062.5 newton meters, and they are the units. 1062.5 Newton meters, and it's actually quite important that you get the hang of that idea. I'll show you why. Weight equals mass times gravity, the one that we did up here, just above. Let's look at that. The units are newtons, they're already given to us, but what if they weren't? Well, I happen to know it's newtons, that's fine, but I could also write 150 kilograms meters seconds to the -2. That's the correct answer as well, because this is what a newton is. So you don't actually have to do anything with the units. The reason we leave them hanging around like that is so we know where the number came from. Just a useful bit of information for you. You didn't need to worry about it in this question because it gave it to you. But if it ever doesn't and you're not sure what the units are, just put them all at the end. Everything being multiplied through comes out at the end. If you're dividing, put a negative sign up in the top. There we are. 3. A heavier child wants to sit on the tyre. Describe how the tyre position should be adjusted so that the moment is the same as in B2. Alright. Well, let's look at that. We know the moment is force times distance. And we want them to be the same before and after. F1, D1, F2, D2. Alright, so what's it telling us? If I want these to have the same value, and I'm going to use a larger child, a heavier child. There we are. If I'm increasing that force, then the only way it'll be equal to each other is if I decrease the distance. And there we go, that's the answer. Reduce the distance, so the swing is closer to the tree. So reduce the distance of the swing along the branch, make it closer to the tree. There we go. Reduce distance of swing along branch, make it closer to the tree. 4. Figure 4.1 shows a hydroelectric power system located in the mountains. The reservoirs store energy. Technically they store water. Sorry. The reservoirs store energy. State the terms used to describe the energy stored in the reservoir. State the term used to describe the energy that the water has because of its position in the reservoir. There we go. And the answer is gravitational potential energy. GPE, gravitational potential energy. B. Describe how the energy stored in reservoir C becomes useful energy for the city at the hydroelectric station. Alright, well, how the energy stored in C, how the water can be used to generate electricity is what it's asking. Well, the water travels down here. As it travels down, it speeds up, and it turns the turbines at the bottom, and the turbines then turn the generator, and then happy electricity. Okay, so we need to put that into proper words. Happy electricity will not get you any marks, just so we're clear. So, as water flows down the pipe, the gravitational potential energy changes to kinetic energy. Alright, you know what I'm going to do? I'm going to take this and I'm going to answer this using the approach I always do, which is something happens which has an effect, which means therefore. Okay, so something happens. Water flows down the pipe, which has an effect. The gravitational potential energy stored in the water changes to kinetic energy, which means, well, the kinetic energy of the water turns the turbine, passes its kinetic energy onto the kinetic energy of the turbine. So which means the kinetic energy of the water turns the turbine, giving it kinetic energy. Therefore, well, the turbine is connected to the generator, so that will also turn and generate electricity. There we go. Something happens which has an effect, which means therefore. And now what I just like to do for these kind of energy questions is I just put something down here. So gravitational potential energy of the water changes to kinetic energy of the water, changes to kinetic energy of the turbine, changes to kinetic energy of the generator, so it turns round, which changes to electrical energy. Just a little diagram to show what I'm talking about above. Problem solved. Next one. Oh, some of the stored energy is wasted. Explain what happens to this energy. Well, as it's travelling down, it actually gets warmer. And the water will lose this warmth to the surroundings. So C. So it's lost its heat to the surroundings. That's what happens to it. And that's one of the main ways that electricity is lost. It tends to be lost as heat. And it's normally heat and sound tend to be the two, but heat's the bigger contributor. Water from reservoirs A and B may flow into C. It is more efficient to fill reservoir C using water from reservoir B only. Suggest a reason for this. Well, let's have a quick look at them. Why use B and not C? Well, why use B and not A? If I use A, I have to actually pump the water upwards. If I use B, it's already above. I just open the valve and it fills reservoir C up. Much easier. I don't have to put energy into the system to do that. So, reservoir A has to be pumped to C, whereas reservoir B has more gravitational potential energy than C, and it can be released directly to C. There we go. So reservoir A has to be pumped to C, reservoir B has more gravitational potential energy than C and can be released directly to C. 5. A laboratory floor has a surface that prevents people from slipping when the floor is wet. Name the force that prevents a person from slipping. That's friction. Which is why it gets so problematic on ice. B. A stool has a round non-slip pad fitted to the bottom of each leg. The stool has 4 legs. The area of each pad is 3 centimeters squared. The weight of the stool is 75 newtons. And the student sits on the stool. The weight of the student is 525 newtons. Calculate the pressure on the floor due to the student and the stool. Alright, first things first. Let's write our equation for pressure. Pressure equals force over area. Why is that important? Well, let's find out what the force is. The force is given by 75 newtons for the stool plus 525 newtons for the student, which is a nice round 600 newtons. The area of each pad is 3 centimeters squared. I'm going to assume when it says pad it means the bit at the bottom of the the bit at the bottom of the stool legs. So the area equals 3 centimeters squared times the 4 legs. So it's 3 centimeters squared per leg. And that will give me 12 centimeters squared. Now normally when we do pressure we do it in pascals. It's force divided by the area, and the area is in meters squared, but look here, they're happy for it to be in centimeters squared. That's good. That makes our lives much easier. So let's use that. Pressure equals force over area. That's 600 newtons divided by 12 centimeters squared, which will give me a value of 50 newtons per centimeter squared. There we are. That's our answer, 50. So a key point there, pay attention to the units. That's made our lives easier, the fact we could do it like that. Part 2. The legs of a stool are made of hollow metal tubes. Figure 5.1 shows the bottom of a stool leg with and without a pad. Explain why a stool leg without a pad does more damage to the floor. Well, pretty straightforward. We know pressure is force over area. Without a pad, there's less area. Less area, more pressure. So pressure equals force over area, as the area without the pad is smaller. The pressure would be bigger. And the legs could scratch the floor. There we go. And that's just purely because pressure is force over area. As the area gets smaller, the pressure will get bigger. There we go. Question 6. Figure 6.1 shows workers pouring liquid metal. The metal changes from a hot liquid to a cool solid. Describe what happens to the arrangement, separation and motion of the atoms as the metal changes from a hot liquid to a cool solid. Right. Well, a few things are going to happen. As the temperature drops, the kinetic energy is going to drop, so the molecules vibrate much less. As it's going from a liquid to a solid, the molecules are going to get closer together. And the molecules are going to take up fixed positions and really vibrate about those positions. So let's try and write that down. Something happens which has an effect, which means therefore. So something happens, the molecules vibrate less. As they vibrate less, their separation between them decreases because they need less space. They're not moving around as much, knocking into each other. So the separation between them decreases. So what then? Well, as the separation decreases, they're taking up fixed positions. And as they've taken up fixed positions, the molecules now vibrate about those positions. B. The workers cool their tools in water. They spill some water onto the floor, but later the floor is dry. Explain what happens to the water and state the name of the process. Okay, well, what's happening in this case is evaporation. Certainly I can label that down here now. The water's evaporated. So what's happening here? Well, water can gain energy from its surroundings. And the water molecules have a range of kinetic energy, with some water molecules near the surface able to escape. They've got so much kinetic energy, and they take away more than the average, and it cools down the remaining water. So water can gain energy from its surroundings. So some water molecules near the surface of the liquid have enough kinetic energy to escape the water and become gas. So this will reduce the temperature of the water, but the water gains more energy from its surroundings. And because it can gain more energy from its surroundings, the process continues until there's none left and it's all evaporated away. Alright, electromagnetic spectrum question. And complete figure 7.1 by adding 2 missing labels. Radio waves, microwaves, infrared radiation, visible light, something, gamma rays. Okay. Well, here, X-rays. And here, UV light, or UV radiation. Now part B, state a use of infrared radiation. Oh, here we go. How about TV remote controls? There we go. And you could also have them in heaters and incubators. And part C, describe the harmful effects of microwaves on people. Well, hopefully none. Hopefully you're not close enough to get it. Unless someone's building a microwave death ray, you should be fine. Mostly your microwaves are protected against these kind of things by those little metal holes. All the microwaves should be stored inside. So if they did get out, however, what would happen is it would heat up cells inside the body. There we go. Can heat cells inside the body, but outside of a microwave death ray, you're pretty fine. Obviously, never use a broken microwave. 8. Iodine-131 is a radioactive isotope of iodine. Iodine-131 decays by the emission of a beta particle and a gamma ray. Okay, nucleus of iodine-131 can be represented as that. Determine the number of neutrons in a nucleus of iodine-131. Okay, well, the neutrons will be given by 131 minus 53. 53 is the number of protons, and 131 is protons plus neutrons. Easy, 78. So 78 neutrons. Beta particles and gamma rays are ionizing radiations. Explain the meaning of ionizing radiations. Well, radiations have so much energy they knock out electrons as they pass by if they get too close to an atom or a molecule. So radiation that removes electrons, specifically what it does is it creates ions because it's knocked the electrons out. That's why it's called ionizing. Right, figure 8.1 shows a decay curve for iodine-131. We have count rates on the left and time and days on the right. Use the information to determine the half-life of iodine-131. Alright, the half-life will be given when 32,000 changes to 16,000. The length of time that takes for it to become a half of its radioactivity. And that should be the same value as the length of time it takes to become 8,000 and for 8,000 to become 4,000. So if these numbers match up, then we know we've got the half-life. Alright, 32,000 to 16,000. Here we go. It says 8 days. And if there were different numbers, you might take the average. So 16 to 8,000. Here we go. That's from here 8 days to 16 days. That's another 8 days. And I'm guessing that the last one, 4,000, 8,000 to 4,000, will be most likely, there we go, 24, 8 days. Show clearly how you've used the graph. Right. So I've drawn lines on the graph. It's pretty clear what I'm doing. I've got a little section there. What I'll do is count, and I'll put time to reduce by half. Which is a half-life. And there we go, that pretty much shows exactly how I got the information. I might just write it out a little bit, just to make sure there's no ambiguity and to make sure that I'm getting the marks. And just to show I understand what I'm doing, I'm just going to put the average is 8 plus 8 plus 8 divided by 3, which is 8 days. That's just to show what I would do if the numbers were different, or if there was inconsistencies in them. So half-life, 8 days. Problem solved. D. A different radioactive substance has a half-life of 120 hours. Calculate the time for it to decay to 25% of its original amount. Alright, let's just look at this. From 100% to 50% is one half-life. From 50% to 25% is one half-life. So that means that to go from 100% to 25%, I would need to take up 2 half-lives. So if each half-life is 120 hours, to go from 100% to 25% would be 120 hours times 2, which is 240 hours. Excellent. Let's move on to 9. Question 9. Figure 9.1 shows a position of a man working in a rock quarry. A single explosion is used to break part of one rock face. Explain why the man sees a flash of the explosion before he hears the bang. Now, the reason for that is that light travels much, much faster than sound. So light travels much faster than sound. B. The man hears a second bang shortly after the first bang. State the name given to the second bang. Well, that is an echo. And state how the second bang compares to the first bang in terms of its amplitude and speed. Well, it's not going to be as loud, so the amplitude is smaller. And speed, what's the speed of sound in air? It's exactly the same. The man stands 170 meters from the back rock face. The time between hearing the first bang and hearing the second bang is 1.0 seconds. Use the information in figure 9.1 to determine the speed of the sound in the quarry. Okay, let's look at that. So what happens is the man hears the sound as it reaches him. There we go. But he also hears the sound 1 second later as it hits the rock face behind him and bounces back. There we are. So what does that mean? If this is a distance d, then sound has to travel to the rock face, d, and back from the rock face, another d, before reaching the man. And we're being told that the distance of the rock face from the man is 170 meters. In fact, it's there in the diagram. Okay, so now we need to use our equation for speed. Speed is distance over time. And the distance travelled is 170 meters towards the rock face and another 170 meters back. Divided by the time, which is 1.0 seconds, and that will give us 340 meters divided by 1 second, well, 1.0 seconds, which is 340 meters per second. So the speed of sound is 340 nanometers per second. The units are already there. Excellent. Figure 10.1 shows a demonstration with magnets. The strong magnet has a pole on its top surface and a pole on its bottom surface. The strong magnet is placed above a small magnet that's connected to the bench by a string. Explain why the magnet is in the position shown in figure 10.1. Alright, well, what's going to happen is it's attracted by the big magnet, and you're going to have a situation where the opposite poles are near each other. You've got a north and a south attracting, or a south and a north attracting. The strong magnet is turned so that the opposite surface is now facing the small magnet. State and explain what happens, if anything. Well, now you've got a situation where you had opposite poles, now you've got the same poles, and the same poles repel each other. So the small magnet will be repelled and will fall to the surface of the bench. B1. Describe a method for magnetizing an ion pin using a permanent magnet. Okay, just going to do a couple of things here. Thing number one. No. What this question is asking is how you magnetize an ion pin. The key thing to understand here is the question should really say a steel pin. The reason why is for magnetizing a steel pin, it's nice and clear, nice and straightforward. Iron is soft, it's a softly magnetic material, a soft magnetic material. So it doesn't hold its magnetism. So you don't magnetize it using a permanent magnet in the same way. And I had a look at the answer to this earlier on, so it's actually incorrect, it's wrong. As it goes, the question itself, it's not a winner. You can magnetize an ion pin just by putting a permanent magnet near it. That's absolutely fine. But the answer is talking about creating a permanent magnet. So the question here, as I say, it's not a good one. Unfortunately, CIE have let us down for this question. Not a problem when things like this go wrong, and they do happen time to time in exams. If there's a question which is not done right, which is has got errors in it, then what happens is they extend the marks for which they'll give a correct answer. Extend their nets, if you like, for giving correct answers. Okay, so what happens, and I'll deal with how you magnetize a steel pin using a permanent magnet. And what you do is you basically stroke it in the same direction several times using a strong permanent magnet. So you stroke it in the same direction several times using a strong permanent magnet, and that will magnetize a steel pin. An iron pin doesn't get magnetized like that because it's a soft magnetic material, it doesn't hold the magnetism. And of course, if we look at ion filings, we can prove that that's what happens. The ion filings will become magnetized, and while the magnet is next to them, the moment you take that magnet away, they just go back to normal. So there we go, that's the answer they were looking for that question. But CIE, do better next time, because the answer is wrong when you're dealing with an ion pin. Alright, B2. Explain how you would identify the poles of the magnet made in B1. Well, you use a magnet with a known north and south and see which side attracts. The south will attract north and vice versa. Question 11. Figure 11.1 shows a power supply in series with a resistance wire and a switch. When the switch is closed, energy is transferred from the power supply. Explain what happens to this energy. Alright, well what's going to happen to the energy is the electrical energy is converted to thermal energy, converted to heating the wire. And then, over time, that'll be lost to the surrounding air. So let's put that down. So the energy heats wire and it's then lost to the surrounding air. B, a student wants to determine the resistance of the wire. He adds a component to the circuit shown in figure 11.1 and he measures the current in the circuit. State the name of the component he uses. Well, the thing that measures the current is of course an ammeter. 2. The student measures the potential difference across the resistance wire. Draw the correct symbol for the component he uses and show how he connects it. Alright, potential difference is the voltage. So to measure that, he's going to need a voltmeter. And that's across the resistance wire. There we go, beautiful. Across the resistance wire. 3. Figure 11.2 shows the symbol for another component that the student adds to the circuit. State the name and function of this component. So this is a variable resistor. And the function, well, it can be used to change the resistance in the circuit. There we are. Question 12. A student demonstrates electromagnetic induction. A. Describe how to demonstrate electromagnetic induction using a magnet, a coil of wire and a sensitive ammeter. You may include a diagram. Okay, let's look at this. What we have is a coil of wire. And an ammeter. So we get a magnet as well. I'll just draw with a north and a south so it's clear it's a magnet. Now let's label this. A is for ammeter. The reason I'm labeling it is because it's not a circuit diagram. So I just want to be clear as to what everything is. And this is a magnet. Here, okay. So let's break it down. Using the setup above. A magnet is brought close to the coil and inserted inside. And the ammeter will show an induced current. And that's it, that's all you need to do. State two factors that affect the size of an induced current, or electromotive force. Well, two things. Number of coils is a good one. Something else, strength of the magnetic field. And I'll put down another one as well. Just to prove there's more than two. Speed of the magnet would do it. There we go. Excellent, well done. I hope you enjoyed the video. If you like it, well, please feel free to like and subscribe. I'll try and get out about 5 videos a week if possible. Have an awesome day.